For 400 years, science has operated on a single, quiet agreement. An agreement so fundamental that it is almost never spoken aloud because questioning it feels like questioning the ground beneath your feet. The agreement is this: there is nothing special about where we are. The Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. The galaxy is not the centre of the universe. We are nowhere in particular, floating in an unremarkable corner of an unremarkable galaxy in an ocean of 2 trillion others. This idea has a name. It is called the Copernican principle, and it is not just a philosophical preference, it is the mathematical foundation on which the entire modern model of the universe is built. Every equation we use to describe the Big Bang, every calculation that tells us the age of the cosmos, every model that predicts how galaxies form and how space expands, all of it depends on one non-negotiable assumption. The universe is the same in every direction. There is no up, no down, no left, no right, no preferred axis, no special orientation. If you could stand at any point in the observable universe and look outward, the view should be statistically identical no matter which way you turn. Physicists call this isotropy, and it is not optional. If isotropy fails, the equations fail. If the equations fail, everything we think we know about cosmology falls apart. Before we begin, if you're kind enough, a gentle like and tap on subscribe would mean the world to me. It's a small gesture, but I hold it with deep gratitude, because every bit of your support keeps this tiny universe alive. To test whether the universe truly is the same in every direction, scientists use the oldest light in existence. It is called the cosmic microwave background. It is not starlight. It is not the glow of galaxies. It is the afterglow of the Big Bang itself, released 380,000 years after the birth of the universe, when the primordial plasma cooled just enough for photons to travel freely for the first time. That light has been travelling through space ever since. For 13.8 billion years it has crossed the expanding void, stretched by the growth of the universe from visible light into microwaves, cooling from thousands of degrees to just 2.7 degrees above absolute zero. It fills every cubic centimetre of space. It comes from every direction. It is the most ancient signal the universe has ever produced, and it is the closest thing we have to a baby photograph of all of existence. When you look at a map of the cosmic microwave background, it appears as a speckled, chaotic pattern of slightly warmer and slightly cooler regions. The temperature differences are extraordinarily small, roughly 1 part in 100,000. To a cosmologist, this near uniformity is beautiful. It is confirmation that the early universe was smooth, well mixed, and isotropic, exactly as the equations require. But the tiny variations, the subtle patches of hot and cold, are not random noise. They are the fingerprints of quantum fluctuations from the first trillionth of a second of existence, stretched across the sky by the expansion of the universe. They are the seeds that eventually grew into every galaxy, every star, every planet, every atom of your body. And when scientists began to study these variations with the precision that modern satellites could provide, they found something that should not be there. The tool they used is called multipole expansion. Think of it as breaking a complex sound into its individual notes. The cosmic microwave background is like a chord played on a cosmic instrument. Multipole expansion separates that chord into its component frequencies. The first note is the dipole, a simple hot on one side, cold on the other pattern, caused by the motion of our galaxy through space at roughly 370 kilometers per second. Scientists subtract this out. It is a known local effect. It tells us nothing about the universe at large. The next note is the quadrupole. This represents the temperature pattern on the largest possible scale, dividing the sky into 4 broad regions of hot and cold. After that comes the octupole, which divides the sky into 8 regions. In a universe that began with random quantum fluctuations inflated to cosmic size, these 2 patterns should have absolutely nothing to do with each other. They were set during different moments of the inflationary epoch. They are products of independent quantum processes. There is no physical mechanism in the standard model that would cause them to be aligned. Expecting the quadrupole and the octupole to point in the same direction is like expecting two strangers on opposite sides of the planet to flip a coin at the same moment and have both coins land on the same edge. Not just unlikely, physically unmotivated. There is no reason for it to happen. In 2005, researchers analysing data from the Wilkinson Microwave Anisotropy probe, known as WMAP, the most advanced microwave satellite ever launched at that time, measured the orientation of the quadrupole and the octupole. What they found was a statistical anomaly that defied every expectation. The two patterns were almost perfectly aligned. They were stacked on top of each other, pointing in the same direction across the sky, forming a single, coherent axis through the cosmos. The probability of this alignment occurring by chance in a truly isotropic universe was calculated to be less than 0.1%. In physics, when something has a 99.9% probability of not being a coincidence, it demands an explanation. Cosmologist João Magajo gave it a name. He called it the axis of evil, not because it was literally evil, but because of the damage it does to our theories. If the largest temperature structures in the 13.8 billion-year-old universe are aligned along a single axis, it means the universe has a preferred direction. It means isotropy is violated. It means the Copernican principle, the bedrock assumption of 4 centuries of science, might be wrong. But that was not the worst part. The worst part was where the axis pointed. When the researchers projected this cosmic axis onto a map of our own sky, they found that it was aligned with the ecliptic plane of our solar system. The ecliptic is the plane of the Earth's orbit around the Sun. It is the flat disk that the planets trace out as they circle our star. It is a local feature, a property of our tiny, insignificant corner of space, and somehow the largest structures in the oldest light in the universe, patterns set in motion nearly 14 billion years ago, long before our Sun existed, long before our galaxy had finished forming, long before the atoms that make up the Earth had been forged in the furnaces of dying stars, appear to be oriented along the same plane as the orbit of a small, rocky planet around a middle-aged star in a quiet arm of an ordinary spiral galaxy. The cosmic microwave background was imprinted 380,000 years after the Big Bang. Our solar system formed 9.2 billion years later. There is no mechanism in any known physics that could connect the two. There is no force, no field, no interaction that could cause a pattern from the dawn of time to align with the orbital plane of a planet that would not exist for another 9 billion years. And yet, the data showed exactly that. The axis of the quadrupole and the axis of the octupole aligned with each other and aligned with us. Lawrence Krauss, one of the most prominent cosmologists in the world, responded to the finding with a statement that captured the unease of the entire field. He said, "The results are either telling us that all of science is wrong and we are the centre of the universe, or maybe the data is simply incorrect, or maybe there is something weird about the microwave background results, and that maybe there is something wrong with our theories on the larger scales." The scientific community chose to believe it was a mistake. They assumed the WMAP satellite had a subtle instrumental bias. They assumed the process of subtracting the Milky Way's own radiation from the data had left behind a ghost, a residual smear that happened to align with the ecliptic because the Milky Way sits roughly on the same plane. They assumed that with better technology, the axis would vanish. They waited for the next generation of satellite. They waited for the European Space Agency's Planck mission, launched in 2009 with the most sophisticated microwave detectors ever built, operating across a wider range of frequencies with dramatically better sensitivity and resolution. Planck would settle it. Planck would make the axis disappear. Planck would save the Copernican principle. Planck did not save anything. When the first major release of Planck data arrived in 2013 and was subsequently refined in 2015 and 2018, the axis was still there. The alignment between the quadrupole and the octupole was confirmed. The correlation with the ecliptic was confirmed. The anomaly had survived the transition from one satellite to another, from one set of instruments to a completely different set, from one frequency range to multiple frequency ranges. If the axis were merely a shadow of the Milky Way's dust, it should have looked different at different frequencies. It did not. The signal was consistent, robust, reproducible. Two independent satellites, built by different space agencies, using different technologies, separated by nearly a decade, had seen the same thing. The easy answers were gone. The comfortable explanations had been tested and had failed. The axis of evil was not a smudge on the lens. It was not a ghost left behind by imperfect data processing. It was a feature of the oldest light in the universe, confirmed to a level of precision that left the scientific community with a choice it did not want to face. Either our statistical methods are failing us in a very specific and unprecedented way, or the universe is not the smooth, directionless, featureless void we have spent 400 years believing it to be. And that was before the supporting evidence started arriving from completely independent sources. That was before the galaxies started moving in the same direction. That was before the black hole started spinning the same way. That was before the axis of evil stopped being an isolated anomaly and started looking like the first visible thread of a pattern woven into the fabric of the cosmos itself. Whenever a measurement threatens to overturn everything we know about physics, the first response of the scientific community is not excitement. It is not wonder. It is not the romantic image of scientists gasping at a blackboard. It is suspicion. Deep, methodical, relentless suspicion. Because the history of science is littered with anomalies that turned out to be errors, signals that turned out to be noise, patterns that turned out to be the product of the human brain's compulsive need to find order in chaos. And so, when the axis of evil appeared in the data, the physics community did exactly what it was trained to do. It tried to kill it. The most immediate and most intuitive explanation was foreground contamination. The cosmic microwave background is the oldest light in the universe, but to see it, our satellites have to look through everything that sits between us and the edge of the observable universe. And the biggest obstacle is our own galaxy. The Milky Way is not a quiet, transparent structure. It is a chaotic, luminous, dust-choked disk of stars and gas that emits its own radiation across a wide range of frequencies. Synchrotron emission from high-speed electrons spiraling through magnetic fields. Thermal emission from dust grains heated by starlight in active star-forming regions. Free emission from ionized hydrogen gas. All of this galactic noise sits in the foreground, between us and the cosmic microwave background, and it has to be subtracted before the primordial signal can be analysed. This subtraction process is called cleaning the map. It is extraordinarily sophisticated. Scientists use observations at multiple frequencies to distinguish the spectral signature of galactic emissions from the spectral signature of the cosmic microwave background. Each type of contamination has a characteristic frequency profile. Dust is brightest at high frequencies. Synchrotron emission dominates at low frequencies. The CMB itself has a specific blackbody spectrum that is different from all of them. By combining observations across many frequency channels, scientists can, in principle, peel away the layers of galactic noise and isolate the primordial signal beneath. But if this process is even slightly imperfect, the geometry of the Milky Way can leak into the cleaned maps. And here is the critical point. The Milky Way sits roughly on the same plane as our solar system. The galactic disk and the ecliptic plane are not identical. They are tilted about 60 degrees relative to each other. But the concern was that residual galactic contamination might create a false alignment that happened to correlate with the ecliptic. If the dust subtraction left behind a faint shadow of the Milky Way structure, that shadow would naturally have a preferred orientation. And that orientation could, in principle, mimic a cosmic axis. This was a serious and legitimate concern. Scientists spent years testing it. They varied the cleaning methods. They used different frequency combinations. They applied different galactic masks, blocking out more or less of the Milky Way to see how the axis responded. They tested the results using component separation algorithms with names like SMICA, NILC, SEVEM, and Commander, each one approaching the problem from a different mathematical angle. The axis persisted through all of them. When the Planck satellite observed the sky at 9 different frequency channels, ranging from 30 GHz to 857 GHz, the alignment was present across the full range. If the signal were galactic dust, it should have looked dramatically different at 30 GHz than at 857 GHz. It did not. The spectral behaviour of the axis was consistent with a cosmological signal, not a foreground artifact. The second line of attack was the kinematic quadrupole. Our solar system is not stationary. It is moving through space at approximately 370 km per second, relative to the cosmic microwave background. This motion creates the dipole, the large-scale hot on one side, cold on the other pattern that is the first thing scientists subtract from the raw data. But the subtraction of the dipole is not perfectly clean. There is a secondary effect called the kinematic quadrupole, a small distortion of the higher multipoles caused by the interaction between our motion and the primordial signal. If the correction for our motion is not mathematically perfect, it can leak a small amount of directional bias into the quadrupole and octopole, potentially forcing them into an artificial alignment. Scientists tested this as well. They varied the parameters of the dipole subtraction. They modelled the kinematic contribution with increasing precision. They simulated thousands of random universes and applied the same subtraction process to see how often a false alignment would appear. The result was clear. The kinematic quadrupole contributes a small correction to the measured multipoles, but it is not large enough to explain the observed alignment. Even after accounting for every known kinematic effect, the axis remained. The third objection was the galactic mask. Because the centre of the Milky Way is so bright at microwave frequencies that the cosmic microwave background is completely obscured behind it, cosmologists cut a wide strip out of the middle of the sky before performing their analysis. This mask removes roughly 20 to 30% of the sky from the data, and when you remove a large chunk of data from any statistical analysis, you change the properties of the analysis itself. Critics argued that the specific shape of the mask might be distorting the multipole decomposition, squeezing the mathematical fit in a way that forces the quadrupole and octopole into an alignment that does not exist in the full sky. This is a subtle and technically demanding objection, and it was taken seriously. Researchers tested different mask sizes. They tested different mask shapes. They used in-painting techniques to fill in the masked region with statistically plausible simulated data, and then repeated the analysis. They performed the multipole decomposition on the full sky, using Bayesian reconstruction methods that account for the missing data probabilistically. The results varied slightly depending on the method, but the core finding was robust. The alignment between the quadrupole and the octopole was not an artifact of the mask. It was present regardless of how the masked region was treated. The fourth, and perhaps the most philosophically interesting objection, is the look elsewhere effect. This is a statistical principle that states if you search a large enough dataset for long enough, you will eventually find a pattern that appears impossibly unlikely. The human brain is evolved to detect patterns. It is evolved to find faces in clouds and signals in static. If you test enough statistical properties of the cosmic microwave background, some of them will appear anomalous simply by chance. The question is not whether any anomaly exists. The question is whether this specific anomaly is significant after accounting for all the other tests that were performed and all the other patterns that could have been flagged. The skeptics have a point. If the axis had aligned with the galactic North Pole instead of the ecliptic, we would still have called it strange. If it had aligned with the direction of the Virgo cluster or the Great Attractor, we would have written papers about it. There are many possible directions in the sky that would have triggered excitement. The probability that the axis aligns with any interesting direction might be higher than the probability that it aligns with one specific direction. This is a valid statistical argument, and it has not been fully resolved. But there is a counter-argument that has grown stronger with time. Because the axis of evil is no longer alone, if the alignment between the quadrupole and the octopole were the only strange thing in the data, the look elsewhere effect might be enough to explain it away. A single anomaly, no matter how striking, can always be attributed to chance, if you are willing to accept that unlikely things sometimes happen. But what has changed the conversation? What has shifted the weight of the debate from skepticism toward genuine concern is that the cosmic microwave background is no longer the only place where a preferred direction has been found. By 2024 and 2025, independent observations from completely different instruments, studying completely different phenomena, began to converge on the same conclusion. The universe appears to have a direction, and it shows up everywhere we look. The first piece of independent evidence came from dark flow. By studying the kinetic Sunyaev-Zeldovich effect, the way cosmic microwave background photons are scattered by the hot gas inside galaxy clusters, astronomers discovered something deeply unsettling. Thousands of galaxy clusters, separated by vast distances, appeared to be streaming at enormous velocities toward a specific patch of the sky. This motion could not be explained by the expansion of the universe. It could not be explained by the gravitational pull of any known mass within the observable universe. It was a coherent, large-scale flow of matter in a direction that should not exist if the universe is truly isotropic. And the direction of this dark flow was roughly consistent with the axis of evil. The second piece came from quasars. Quasars are the intensely luminous cores of distant galaxies, powered by supermassive black holes consuming matter at extraordinary rates. Because they are visible across billions of light years, they serve as markers for the large-scale structure of the cosmos. In studies conducted between 2022 and 2025, researchers found that the spin axes of quasars are not randomly oriented. They are aligned with each other over distances of billions of light years, and these alignments follow the same directional pattern as the axis in the cosmic microwave background. There is no known mechanism that should cause a black hole in one corner of the observable universe to align its spin with a black hole in another corner, unless both were influenced by the same underlying structure. Unless the universe itself has a grain to it, a texture, a direction that was imprinted at the moment of its birth and has persisted ever since, written into the temperature of the oldest light, the motion of galaxy clusters, and the rotation of the most powerful objects in existence. When you take the CMB data, the dark flow data, and the quasar alignment data together, the probability of all three pointing in the same direction by random chance approaches zero. This is what scientists call a multi-messenger signal. It is no longer a single anomaly in a single satellite's map. It is a consistent directional bias that shows up in the temperature of the early universe, the motion of modern galaxy clusters, and the orientation of ancient black holes. Three independent messengers, three independent instruments, three independent epochs of cosmic history, all pointing the same way. The coincidence has become too large to ignore, and the question is no longer whether the axis is real. The question is what it means. The axis of evil does not exist in isolation. It is not a single crack in an otherwise perfect wall. It is one of several fractures that have appeared across the surface of modern cosmology over the past 2 decades, each one small enough to ignore on its own, but together forming a pattern that is becoming increasingly difficult to dismiss. The standard model of cosmology, the framework known as lambda CDM, has been the most successful scientific model ever constructed for describing the large-scale behavior of the universe. It has predicted the cosmic microwave background with breathtaking accuracy. It has explained the distribution of galaxies across billions of light years. It has accounted for the accelerating expansion of the universe and the relative abundances of hydrogen and helium produced in the first minutes after the Big Bang. But it is built on assumptions, and those assumptions are beginning to show stress fractures that no amount of precision can smooth over. The most famous of these fractures is the Hubble tension. For years, scientists have been measuring the expansion rate of the universe using 2 fundamentally different methods, and the 2 methods will not agree. The first method uses the cosmic microwave background. By analysing the patterns in the oldest light in the universe and feeding them through the equations of lambda CDM, scientists can calculate how fast the universe should be expanding today. The answer is approximately 67.4 kilometers per second per megaparsec. The second method uses the cosmic distance ladder. By measuring the distances and velocities of nearby objects, Cepheid variable stars, Type 1a supernovae, galaxies whose distances can be calibrated step by step, scientists can directly observe how fast the universe is expanding right now. The answer is approximately 73.5 kilometers per second per megaparsec. The difference is roughly 9%. For years, cosmologists hoped this was a measurement error. Perhaps one team had miscalibrated their instruments. Perhaps there was a systematic bias in the supernova data. Perhaps the Cepheid variables were not as reliable as we thought. But as of 2026, the gap has only widened. Every new measurement, every refined calibration, every independent cross-check has pushed the two numbers further apart rather than closer together. The Hubble tension is no longer a discrepancy. It is a crisis. And here is where the axis of evil becomes something far larger than an anomaly in a microwave map. Because there is a growing body of theoretical work suggesting that the Hubble tension and the axis of evil may be symptoms of the same underlying problem. The connection is elegant and disturbing. Lambda CDM assumes the universe is isotropic. It assumes the expansion rate is the same in every direction. But if the universe has a preferred direction, if space itself has a grain to it, then the expansion rate would not be uniform. It would vary depending on which direction you measured it. If we happen to be sitting in a region of space that is expanding slightly differently from the average, or if we are measuring the expansion along an axis that is not representative of the whole, our numbers would never match. The cosmic microwave background method, which averages over the entire sky, would give one answer. The distance ladder method, which measures objects along specific lines of sight, would give another. The axis of evil is the directional evidence. The Hubble tension is the speed evidence. Together, they point toward a universe that is not the smooth, uniform, isotropic sphere that lambda CDM requires it to be. This forces us to confront the most uncomfortable implication of the axis of evil, the potential breakdown of the Copernican principle itself. For 4 centuries, science has progressed by systematically removing humanity from the centre of the narrative. Copernicus moved us away from the centre of the solar system, Galileo confirmed it, Kepler refined it, Newton generalised it. Hubble showed us that our galaxy is one of billions. The cosmic microwave background showed us that the universe looks the same in every direction. Step by step, discovery by discovery, we have built a picture of the cosmos in which our location is utterly unremarkable. Not at the centre, not in a special place, nowhere in particular. The axis of evil threatens to reverse this trajectory. Not because it says we are the centre of the universe, the data does not say that, but because it says the universe has a direction, and that direction appears to be correlated with our solar system. And if it is, then our position is not random, it is not generic, it is somehow connected to the large-scale geometry of the cosmos in a way that no current theory can explain. Some theorists have proposed that we might be located near the centre of a giant cosmic void, a region of space that is slightly less dense than its surroundings. In this scenario, the axis is not a property of the whole universe, but a result of how light travels through the underdense region around us. Light passing through a void is affected differently than light passing through average density space. The void could create a directional bias in the cosmic microwave background that mimics a cosmic axis. This explanation preserves the Copernican principle on the largest scales while explaining the anomaly as a local effect. But it comes with its own costs. If we live in a void, the expansion rate we measure locally would be different from the expansion rate measured by the cosmic microwave background. This would explain the Hubble tension, but it would also mean that what we observe from Earth is a special case rather than a universal truth. Every cosmological measurement we have ever made, every conclusion we have drawn about the age and composition and fate of the universe would need to be recalibrated for our specific location. The laws of physics would still be the same everywhere, but the observations would not. There is another possibility that is even more radical. In 2025, simulations showed that if the universe has a non-trivial topology, if it is not infinite and flat, but finite and wrapped, like a 3-dimensional version of a torus, a donut shape, the axis of evil can be reproduced almost perfectly. In a toroidal universe, space is finite but has no edge. If you travel far enough in one direction, you eventually return to where you started. This wrapping creates preferred directions. If the torus is narrower in one dimension than another, the largest temperature fluctuations in the cosmic microwave background would naturally align along the longest axis. Light from the Big Bang would take multiple paths to reach us, echoing around the shape of the universe, creating correlations between the quadrupole and octopole that would look exactly like the axis of evil. The beauty of this explanation is that it does not require us to be in a special location. The axis would exist for any observer anywhere in the universe. The Copernican principle survives. But the shape of the universe changes. It is no longer the infinite, flat, featureless void that lambda CDM assumes. It is a finite, structured, geometrically complex space that has a topology we have never considered in our standard equations. And then there is the possibility that shakes the foundations deepest. For over a century, general relativity has described the geometry of space using Riemannian geometry, a mathematical framework that assumes the properties of space are the same regardless of the direction you face. But there exists a more general framework called Finsler geometry. In Finslerian spacetime, the fabric of the universe is allowed to be anisotropic. The speed of light, the strength of gravity, the way distances are measured, all of these could vary subtly depending on your orientation. In a Finslerian universe, the axis of evil is not an anomaly. It is a natural consequence of the fundamental structure of space. The grain we see in the cosmic microwave background, the coherent motion of galaxy clusters, the alignment of quasar spins, all of it would be the signature of a universe that is built on anisotropic geometry at the deepest level. This would mean that the assumption of isotropy, the bedrock of 400 years of cosmology, was never correct. It was an approximation, a simplification that worked well enough at the scales we could measure, but that breaks down when we look at the full sky with the precision that modern satellites provide. Each of these explanations carries a different cost. The void model preserves most of our physics, but makes our location special. The toroidal model preserves our location, but changes the shape of the universe. The Finslerian model preserves the shape, but changes the laws of physics themselves. None of them is comfortable. None of them leaves lambda CDM intact, and none of them has been ruled out. The standard model of cosmology is not wrong in the way that a clock is wrong when it shows the wrong time. It is wrong in the way that a map is wrong when it describes a flat Earth. The map works perfectly at small scales. It gets you from your house to the store without error. But extend it far enough, push it to its limits, and the distortions become impossible to ignore. The axis of evil is the distortion. The Hubble tension is the distortion. The dark flow is the distortion. The quasar alignments are the distortion. They are all telling us the same thing. The map is not the territory, and the territory is far stranger than the map allows. There is a moment in the history of every scientific revolution when the old framework has clearly failed, but the new one has not yet arrived. It is an uncomfortable place, a place where the data says something the equations cannot accommodate, where the observations contradict the theory, but no replacement theory exists. We are in that moment right now. The axis of evil, the Hubble tension, the dark flow, the quasar alignments, all of them are telling us that the lambda CDM model is incomplete. But incomplete is not the same as wrong, and replacing it requires something more than evidence against the old framework. It requires a new idea that can explain everything the old model explained, plus the things it cannot. Several candidates have emerged, none of them is proven, all of them are extraordinary. The most conservative proposal does not require new physics at all, it requires a new shape. The standard model assumes the universe is spatially infinite and geometrically flat. This is not because anyone has proven the universe is infinite, it is because the data from the cosmic microwave background is consistent with flatness to within the precision of our measurements. But consistent with is not the same as proof. The universe could be very slightly curved, or it could be flat but finite, and we would not be able to tell the difference with current instruments. If the universe is finite and has a specific topology, its shape would affect how light travels across it. The simplest non-trivial topology is a 3 torus. Imagine taking a cube and connecting opposite faces. If you exit through the top, you re-enter through the bottom. If you exit through the left, you re-enter through the right. The result is a finite space with no boundary. You can travel forever without hitting a wall, but you will eventually pass through the same regions again. In a toroidal universe, the cosmic microwave background would carry the imprint of the topology. Light from the Big Bang would take multiple paths to reach any observer, circling around the finite space and arriving from different directions at different times. This would create correlations between temperature patterns on opposite sides of the sky. It would suppress the largest scale fluctuations because waves longer than the size of the universe cannot exist, and it would create a preferred axis if the torus is not perfectly symmetric, if one dimension is shorter than the others. The quadrupole and octupole would align along the longest dimension, because that is the direction in which the largest fluctuations are allowed to develop. Recent simulations published in 2025 have demonstrated that a 3 torus model can reproduce the observed quadrupole-octupole alignment with remarkable fidelity. The axis of evil in this framework is not an anomaly. It is a signature of the shape of the universe, revealing itself in the oldest light we can see. The implications are staggering. If the universe is a torus, it is finite. It has a size. It has dimensions that can, in principle, be measured. The question of how big is the universe would have an answer. Not infinite, not unknowable, a specific number. The diameter of the smallest dimension of the torus would determine the scale of the anomaly. Current estimates, based on the suppression of large angle correlations in the CMB, suggest that if the universe is toroidal, its smallest dimension could be on the order of the diameter of the observable universe itself. We might be living in a universe that is barely bigger than what we can see. A universe whose edges are not infinitely far away, but just beyond the horizon, wrapped around themselves in a geometry that we have been looking through for 13.8 billion years without realizing it. But if the answer is not shape, it might be something more fundamental. General relativity describes gravity as the curvature of space-time. The mathematical language it uses is Riemannian geometry, a framework developed in the 19th century that assumes space is locally isotropic. At every point, the geometry looks the same in every direction. The speed of light is the same. The strength of gravity is the same. The rules do not change depending on which way you face. Finsler geometry removes this assumption. It is a generalization of Riemannian geometry that allows the properties of space to depend on direction. In a Finslerian universe, the vacuum itself has a grain. Light travelling along one axis could behave subtly differently from light travelling along another. Gravity could be fractionally stronger in one direction than another. The very definition of distance would depend on orientation. This sounds radical, and it is. But Finsler geometry is not new. It was developed by Paul Finsler in 1918, just 3 years after Einstein published general relativity. It has been studied by mathematicians for over a century. What is new is the realization that the observational data might be demanding it. If the cosmic microwave background has a preferred axis, if galaxy clusters are streaming in a preferred direction, if quasar spins are aligned along a preferred orientation, then the simplest explanation within the framework of geometry itself is that spacetime is Finslerian rather than Riemannian. The grain we see in the data is the grain of the vacuum. The axis of evil is not a pattern imprinted on space, it is a property of space. The consequences for physics would be profound. Every equation in general relativity would need to be generalized. The Friedmann equations that describe the expansion of the universe would acquire directional terms. The predictions for gravitational waves, black hole mergers, and the formation of large-scale structure would all change slightly depending on orientation. The Hubble tension could be resolved naturally because the expansion rate would not be isotropic. Different directions of observation would yield different measurements, not because of errors, but because the universe genuinely expands at different rates along different axes. There is a third possibility that sits at the intersection of cosmology and quantum information theory. The holographic principle, first proposed by Gerard 't Hooft and refined by Leonard Susskind in the 1990s, suggests that all the information contained in a three-dimensional volume of space can be encoded on a two-dimensional boundary surrounding that volume. This is not a metaphor. It is a mathematical result derived from the physics of black holes. The entropy of a black hole, the maximum amount of information it can contain, is proportional not to its volume, but to the area of its event horizon. This suggests that the three-dimensional interior is in some sense a projection of information stored on the two-dimensional surface. If the universe itself is holographic, if the three-dimensional space we inhabit is a projection of information encoded on a distant two-dimensional boundary, then the axis of evil could be an artifact of the projection, not a physical line through three-dimensional space, but a feature of how the two-dimensional information is mapped onto the three-dimensional interior. Depending on the geometry of the boundary and the rules of the projection, certain directions in the interior could appear privileged. The axis would be the seam in the hologram, the point where the projection reveals its own structure. This hypothesis gained significant traction in 2025, with new theoretical work connecting holographic cosmology to observed CMB anomalies. If the axis of evil is a holographic artifact, it will be the first direct observational evidence that we live in a projected reality. Not in the science fiction sense, in the mathematical physics sense. The three dimensions of space we move through would be emergent properties of a deeper, lower dimensional structure. The axis would be the first crack in the projection, the first place where the underlying architecture becomes visible through the surface. And finally, there is primordial magnetism. In the first fraction of a second after the Big Bang, the universe was a plasma of quarks, gluons and leptons at temperatures exceeding trillions of degrees. Under certain conditions, this plasma could have generated a coherent magnetic field that stretched across the entire observable universe. A magnetic field has a direction. It has a north pole and a south pole. It creates an axis by its very nature. If such a field existed in the primordial universe, it would have influenced the flow of plasma, the formation of the first structures, and the temperature pattern of the cosmic microwave background. It would have left a permanent imprint on the oldest light in the universe. And it would have influenced the rotation of every galaxy and every quasar that formed afterward, explaining the quasar spin alignments as a relic of the same primordial field that created the axis in the CMB. Each of these explanations opens a different door into a different kind of universe. The torus gives us a finite cosmos with measurable dimensions. Finsler geometry gives us a universe with directional physics. The holographic principle gives us a projected reality with a hidden lower dimensional structure. Primordial magnetism gives us a universe that was magnetized at birth and has carried that signature ever since. They cannot all be correct. Some of them may be partially correct, some may be entirely wrong, but all of them share a single, inescapable conclusion. The universe is not what we thought it was. We began this journey looking for randomness. We pointed our most sensitive instruments at the oldest light in the universe, expecting to find a smooth, featureless isotropic glow, the afterglow of an explosion that had no center, no direction, no preference for one orientation over another. We expected the cosmic microwave background to confirm what 400 years of scientific progress had taught us, that we are ordinary, that our location is generic, that the universe does not know or care where we are. Instead, we found a line that should not exist, a line that connects the largest temperature structures in the oldest light in the cosmos to the orbital plane of a small, rocky planet around a middle-aged star in a quiet spiral arm of a galaxy that is 1 of 2 trillion. And no one can explain why. The axis of evil has now survived 2 decades of scrutiny. It has been tested by 2 independent satellite missions. It has been probed at 9 different frequency channels. It has been subjected to every cleaning method, every mask variation, every statistical test that the most skeptical scientific community in human history can devise. It has not disappeared. It has not weakened. If anything, it has grown stronger as independent observations from dark flow, quasar spin alignments, and large-scale galaxy surveys have converged on the same directional bias. The universe appears to have an orientation, and that orientation appears to be linked to us. This does not mean we are the centre of the universe. That interpretation is too simple and almost certainly wrong. The axis does not point at the Earth. It aligns with the ecliptic, the plane of our orbit around the Sun. This is a direction, not a location. It does not place us at a privileged position. It places us in a privileged orientation. And the distinction matters because a privileged orientation is something that physics can, in principle, explain without invoking miracles or design. A finite topology can create preferred directions. An anisotropic geometry can create preferred directions. A primordial magnetic field can create preferred directions. A holographic boundary can create preferred directions. All of these are natural physical explanations that do not require the Earth to be special. They require the universe to have structure that we have not yet mapped. But there is an honesty that this moment demands. We do not know which explanation is correct. We do not know if any of the current proposals will survive the next generation of data. The Lightbird satellite, a joint mission by the Japan Aerospace Exploration Agency and the European Space Agency, is designed to map the polarization of the cosmic microwave background with unprecedented sensitivity. Its primary target is the B-mode polarization signal, a faint pattern that would confirm the theory of cosmic inflation and reveal the energy scale at which the universe began its exponential expansion. But Lightbird will also provide the cleanest polarization maps of the large-scale CMB ever produced. If the axis of evil is a real physical feature of the primordial universe, it should appear in the polarization data with the same clarity as it appears in the temperature data. If it does, the debate is effectively over. The axis is real. The universe is anisotropic, and the Copernican principle, in its simplest form, is dead. The Simons Observatory, a ground-based CMB experiment located in the Atacama Desert of Chile at an altitude of 5,200 meters, is another instrument that will bear directly on this question. With its array of over 60,000 superconducting detectors, the Simons Observatory will measure the CMB temperature and polarization at small and intermediate angular scales with a precision that surpasses anything currently available. It will also provide new constraints on the large-scale anomalies, including the axis of evil, the hemispherical power asymmetry, and the suppressed quadrupole, by cross-correlating CMB data with galaxy surveys and gravitational lensing maps. If the anomalies persist across all of these independent datasets, the case for new physics becomes overwhelming. And then there is CMBS-4, the next-generation ground-based experiment that will deploy over 500,000 detectors across multiple sites in Chile and the South Pole. CMBS-4 is designed to be the definitive CMB experiment, the one that either confirms the standard model to a level of precision that leaves no room for anomalies, or reveals the cracks that break it apart. Its projected sensitivity to large-scale polarization is sufficient to either detect or rule out most of the theoretical explanations we have discussed. The torus topology, the Finslerian geometry, the primordial magnetic field, all of them make specific predictions about the polarization pattern that CMBS-4 can test. We are living in the intermission between two acts of a scientific drama. The first act began in 2005, when the WMAP satellite revealed an alignment that no one expected. It continued through the Planck confirmation, the dark flow observations, the quasar alignment studies, and the growing realization that the standard model is under more stress than at any point in its history. The second act will begin when the next generation of instruments delivers its verdict. Either the axis of evil will be explained away by a systematic effect so subtle that it has fooled 2 satellites, 3 independent datasets, and 20 years of analysis, or it will be confirmed as a genuine feature of the cosmos. And if it is confirmed, the consequences will ripple through every branch of physics. The equations of general relativity may need to be generalized. The Friedmann-Lemaitre-Robertson-Walker metric, the mathematical backbone of modern cosmology, may need to be replaced with something that accommodates anisotropy. The measurement of the Hubble constant may need to be rethought entirely, with directional corrections that account for the grain of space. The theory of inflation, which predicts the statistical properties of the cosmic microwave background, may need to be modified to produce a universe with a preferred direction. The very concept of a universal law, a law that applies identically everywhere and in every direction, may need to be softened to allow for a cosmos that has structure at the deepest level. Or perhaps the answer is simpler. Perhaps the axis of evil is a final puzzle piece that, once placed correctly, will reveal a picture so different from what we expected that the question itself changes. We have been asking, is the universe the same in every direction? Perhaps the real question is, why did we ever assume it would be? Symmetry is beautiful. Isotropy is elegant. Uniformity is mathematically convenient. But the universe is under no obligation to be beautiful, elegant, or convenient. It is under no obligation to be simple, and it is under no obligation to make us comfortable. For 400 years, the Copernican principle has served as a guardrail against human arrogance. It has reminded us that our intuitions about our own importance are not to be trusted, that the universe is vast and indifferent, and that we are small. This remains true. Nothing about the axis of evil makes us large. Nothing about it makes the universe care about us. But it may mean that the container we live in is not the featureless void we imagined. It may have a shape, a direction, a grain that was set at the moment of its birth and has persisted for 13.8 billion years, written into the temperature of the oldest light, the motion of the largest structures, and the spin of the most distant objects we can see. We started this story by looking for a random, messy afterglow of a chaotic explosion. Instead, we found something that looks like a compass needle, a line drawn across the sky in the oldest light in the universe, pointing in a direction that, by a coincidence so improbable it borders on the absurd, appears to be aligned with the path our planet traces around its star. Whether that needle is pointing toward a new era of physics, or toward a fundamental error in our own perception, is the question that will define cosmology for the next generation. The instruments are being built, the detectors are being cooled, the satellites are being designed, and somewhere out there, in the faint glow of light that has been travelling for 13.8 billion years, the answer is already written. We just have not learned to read it yet. The universe has a direction. It has always had a direction. We are only now building the tools precise enough to see it. And what we see, when we finally look clearly, will either confirm everything we believe or change everything we know. Both possibilities are real. That is the nature of science at the edge.